It will often be necessary to add vectors together. As we mentioned previously, Chapter 4 will cover forces, which are vectors, and the net force, or vector sum of forces acting on an object, will be important. In principle, adding vectors is not difficult, but we must take into account both the magnitude and the direction properties of the vector. The simplest case occurs when the vectors being added are collinear, which means they point along the same direction. Consider the example of a car moving along a straight line. The car first moves with a displacement vector A equals 275 meters due east. The car then moves again in the same direction with a displacement vector B, which equals 125 meters due east. These two vectors add together to give the total displacement vector r of the car. The letter r is used since the total vector is often called the resultant. When the vectors being added are collinear, like the two here, the magnitude of the resultant vector is just the sum of the two vectors. The direction of the resultant is of course in the same direction as the original two displacement vectors. Formally, we would write the vector addition in the following way. Vector r is equal to vector a plus vector b, or vector r is equal to 275 meters due east plus 125 meters due east, which is equal to 400 meters due east. Again, we can simply add the magnitudes in this way only because the two vectors point in the same direction. However, we will encounter many cases where we have to add vectors together that are not collinear. Let's look at another example that occurs quite frequently. This is the case where we wish to add two vectors that are perpendicular to each other. For example, let's say a car first moves with a displacement vector A equals 275 meters due east. The car then turns left and moves with a displacement vector B, which equals 125 meters due north. We wish to find the vector sum of these two, which will give us the resultant displacement vector. Again, the following vector addition statement applies. Vector r is equal to vector a plus vector b. You can clearly see from the figure that the distance r is not simply the sum of the magnitudes of the two vectors a and b. This is because a and b are no longer collinear. However, vectors a and b form the legs of a right triangle where r is the hypotenuse. We can use the Pythagorean theorem to get the length of r. R will be equal to the square root of 275 meters squared plus 125 meters squared, or equal to 302 meters. We can determine the direction of r by specifying the angle theta. Notice that tangent theta is equal to the opposite side over the adjacent side, or in this case the magnitude of b divided by the magnitude of a. Using our calculator, we find theta is equal to 24.4 degrees. A complete description of the car's displacement vector would be 302 meters directed at 24.4 degrees north of east. Now consider the case where we want to add two vectors, but they are not perpendicular to each other. We can't use the Pythagorean theorem to calculate the resultant. Consider the example where a car first moves with a displacement vector A that equals 275 meters due east, and then with a displacement vector B that is 125 meters directed at 55 degrees north of west. If vectors A and B are drawn tail to head, then the resultant vector r is drawn from the tail of the first vector to the head of the last one. The following vector equation is still correct, that vector r is equal to vector a plus vector b. However, here the magnitude of r does not equal the magnitude of a plus the magnitude of b, since vectors a and b are not collinear. And the magnitude of r also does not equal the square root of a squared plus b squared, since a and b are not perpendicular. We must use a different technique to calculate the resultant vector r. One way would be graphically, where we could use a protractor and a ruled straight edge to draw the vectors to scale and measure the resultant length and angles. Alternatively, we could use some of the properties and relationships of geometry and trigonometry that are presented in Appendix E of your textbook or ebook. Such analysis may be fairly simple for the addition of just two vectors as in our example, but may become much more difficult when adding a greater number of vectors. The component method of vector addition, which we will discuss in section 1.8, provides a straightforward technique for handling more difficult problems. The last topic we wish to discuss in this section is vector subtraction. The nice thing about vector subtraction is that it's really just vector addition, where we take advantage of the following properties of vectors. When a vector is multiplied by -1, the magnitude or length of the vector remains constant, but the direction of the vector is reversed. Consider the following example where vector c is equal to vector a plus vector b. Notice that vector a and b are drawn tail to head, and the resultant vector c is drawn from the tail of the first vector to the head of the last one. We could solve the above equation for vector a by subtracting vector b from each side. Thus, vector a is equal to vector c minus vector b, which is an example of vector subtraction. However, we could also write this as vector a equals vector c plus vector minus b, which is again a statement of vector addition. The figure now shows how to calculate vector A by adding vector C to vector minus B. Notice that vector minus B is the same magnitude as vector B, but now points in the opposite direction. Also notice that vectors C and minus B are arranged tail to head, and that vector A is the resultant vector. In the next section, we will look at the component representation of vectors.